Exercise 6. We have stated that v sub alpha plus 1 is equal to A union the power set of v sub alpha. Prove this at least for alpha less than 3. Right, so doing this for alpha less than 3 is a straightforward thing to do, especially, and I forgot about this when I was first doing this exercise, but on page 9, Enderton says that the A equal to V0 is equal to the empty set because in the textbook Elements of Set Theory, we are not going to consider atoms. So all objects that we work on from this point onward, from page 9 onward, they're all sets. Everything, and I mean everything, is a set. Okay, so let's just keep that simplifying assumption all the way over here. It's just something I think is good to highlight early on. I'll put it in purple so it stands out. But anywho, what I'm going to do is we could do this for two ways. We could do this and show this for alpha equals 0, alpha equals 1, alpha equals 2. So I showed for V0, V1, V2, V3, and so on. I think it's more interesting to prove this in all generality. So I'm going to go ahead and do it by induction. So induction, as usual, starts with a base case. And I'm going to say that here alpha equals 0. So let's see, is this true? So v sub alpha plus 1 is going to be v sub 0 plus 1, which is equal to v1, which, as was defined literally, is equal to v0 union the power set of v0, which is equal to A union power set of v0. So, and I'm going to move this down. So our base case checks out. Now let's move on to our inductive hypothesis. So what is our hypothesis? It is that we're going to assume that v sub alpha is equal to A union power set of v sub alpha minus 1, because we're taking this right here, but with one less. For any arbitrary alpha greater than or equal to 0, right? This is sound because our base case holds up. And now let's go ahead and do the inductive step. Okay, so it's a pretty straightforward induction proof. So v sub alpha plus 1 is equal to v sub alpha union power set of v sub alpha. This just by definition. And v sub alpha, by our inductive hypothesis, is equal to A union power set of v sub alpha minus 1, meaning that, move this over here, v sub alpha plus 1 is equal to A union power set v sub alpha minus 1 union power set v sub alpha. The union operation is associative, so using associativity of U, v sub alpha plus 1 is equal to A union power set v sub alpha minus 1 union power set of v sub alpha. Now, recall that v sub alpha is equal to v sub alpha minus 1 union power set of V sub alpha. So V sub alpha is composed of V sub alpha and anything, it's composed of all the elements in V sub alpha minus 1 and the power set of V sub alpha. So it follows logically that V sub alpha minus 1 is a subset of V sub alpha, which tells us by exercise 3, or actually, I'm going to write these out and spell them out. Just in case. Okay. Call the V. Okay. Thus, this is true. So, or rather, by exercise 1-3, V subset of C implies that power set of B is a subset of the power set of C. So, V sub alpha minus 1, subset of V sub alpha, implies that the power set of V sub alpha minus 1 is a subset of the power set of V sub alpha, which implies that the power set of V sub alpha minus 1 union the power set of V sub alpha is just going to be the power set of V sub alpha. So, what now? So V sub alpha plus 1 has to be equal to A union power set of V sub alpha union power set of V sub alpha minus 1, or rather, this is the order we had it in, which by this rule right here is going to be equal to A union power set of V sub alpha. Thus, the induction is complete. And we are done. We have shown that V sub alpha plus 1 is equal to A union the power set of V sub alpha, just as was asked of us. And we proved that for any alpha greater than or equal to 0. Pretty cool. Or rather, oh yeah, for any alpha greater than or equal to 0. All right, hope this was helpful, and I will see you in the next video.